This video is about volume, surface area and capacity. So it improves skills, knowledge and understanding of volume, capacity, surface area, metric units and even factors, properties of 3D objects, volume and surface area of a cone, and even designing packaging, real life experience.
Welcome, everybody. I'm Tony Bearden. I started AIMSEC about 20 years ago. I've long been retired and I'm based in Cambridge, but whenever I can, I like to spend my time. In the last 20 years, I've spent about half my life in Africa. And Tejumade?
Hi, good day, everyone. My name is Tejumade Ogundipe. I work for AIMSEC. I'm the IT coordinator for AIMSEC, so I'm so excited to be here with you. Yeah, thank you.
And I'm Caroline Ainsley. I'm the founder of Bubbly Maths, and my mission in life, I work in Europe. I travel to South Africa whenever I can and other places in the world. And my mission in life is that every child on earth will love learning and enjoy mathematics. And the best way to help them do that is to work with the teachers and the parents because I can only reach a certain amount, but between us, we can reach many, many, many learners.
Now, today we're going to be talking about volume, surface area and capacity and activities that you can do from babies in the bath right through to the school leaving age. So we're going to talk about things like volume, capacity, surface area, the metric units of grams, cubic centimeters and milliliters, and then number work factors, properties of 3D objects, and finally, the volume of the surface area of the cone, which is something that comes quite late in school life when you're doing that. So we believe that the whole learning experience is a spiral. And what we mean by that is that as we learn, we go up and up, up and up, up and up, and we're always able to build on what we've already learned and look down to the stages below. So unless you've got good foundations, preschool and at the lower primary, the students, learners are going to struggle later on. So what we're talking about today is laying the foundations, building up the ideas, through experience and practical work. And so we're going to start with an activity which is suitable for everyone and then go right through different phases up to upper secondary and the school leaving. And we've got quite a lot of activities, and they're listed from the bottom to the top because we've listed them alongside this spiral, and the activities go up from early years, as you see, through to upper secondary. And we're not going to just talk about everyone in detail now because they'll come in the next couple of hours. We'll be discussing them.
Okay, so we want you to take 2 rows. Basically, you'll be wearing 2 caps. So the first one, you'll be a teacher and also a learner. So you'll be able to do the activities pretending that you only know what your learner knows. So when you are acting like your learner, then you pretend as if you only know exactly what your learner knows. So, and I want you to start thinking about it. Then you talk to other teachers, what is on your mind, and about how your learners might discover new ideas doing this activity. So we want you to do that. And you have to record in whatever way that is possible, or any way that you think is meaningful to you as a teacher and also meaningful to your learners. So you want you to talk about the area being the number of unit squares. Look at it. Talk about the area being the number of unit square, and also the volume being the number of units cubed.
So we're thinking, aren't we, Tej, that this is the first sort of experience of young children in 6-7-year-olds, that they learn about area by counting, and they learn about volume by counting, not by formulas or calculation. So Caroline's going to talk about turning packets inside out.
This is something we've done for some time now. Tony, in my world, it was Tony's idea. So I've got this box of pasta, basically a small, and I've cut it up. So it's just a small cuboid. You can make it as big as you like. I've made it small so you can see it on the screen. And I've opened it out so that you can see the net. Now I've still got the flaps there, so you can cut those flaps off if you want. But the beautiful thing about this is you can now fold it inside out and you have a clean net to be working with. You can do the measurements. And and the questions that you would be asking your learners are, what shapes have you got? So if you've actually got them right in front of you, you can see that in this particular case, it's all rectangles. Now, how much do they hold? That these are all conversational questions you can have. And that can be on more than one level. You can actually test it. You can put things inside and compare the different shape boxes and see how much they hold. And there's often a big surprise there. The other thing is you can get boxes that are not empty, get boxes that are full. You can keep just a box of these in your classroom where they're all different weights and different shapes and sizes. And the learners can say, well, okay, I think this one's going to be heavier. They can choose 2 or 3 if you've got a scale in the classroom. Even if you don't, if you've got the weight of them on the packet, which of course you do, then they can estimate without weighing them, and then they can read, and that's a very real life experience, actually reading what the weight is of it, and get some very practical ideas from experience of real life comparisons. So what is the connection between the measures? We've got the cubic centimeters, we've got the mass, and we've got the capacity or the volume. Now, I'm just going to change to my visualizer, and what I have here, as you can see the scale of it, is 1 cubic centimeter. Now it's a very nice size to have, and learners actually are quite fascinated. If everyone can make a cubic centimeter, that's a nice little activity. It's a bit fiddly, but they can do it, or you can with some help. I couldn't find comparisons of that, so I've created a 5 cubic centimeters. It's just 1 cubic centimeter, and I found that a measuring, it's literally a teaspoon, is actually 5 milliliters. So 5 cubic centimeters. If I were to magically, well, if that was ice, I could make a 5 cubic centimeter of ice. It would melt into here with exactly, I'm going to put it on there. So this is 5 milliliters. And now this is actually by design. The scientists, when they created the measurements, I've got 5 milliliters of water in there, H2O, and more or less at sea level. That weighs 5 grams. So 5 cubic centimeters weight is contained within 5 milliliters of water, and that water, that liquid inside there weighs 5 grams. Now, it's not any liquid, it has to be water. It depends how dense the liquid is.
We're going to work towards these ideas. They're quite deep, and we want really the children, young children, to be beginning to discover these ideas for themselves with using containers that are available, and you can collect, and they can play with and pour water from one to another. So Caroline's demonstrated this tiny little 1 cubic centimeter, and that is exactly for that particular substance the same as 1 gram, and the liters are measuring capacity, but this is the connection that we're looking at. The 1 cubic centimeter is 1 gram is 1 milliliter, and Caroline was showing it with 5 cubic centimeters and 5 milliliters. So it's really a matter of what the children can learn through their own experience. And here, free play is good early learning experience for babies and small children. And so you see these cups on the left there, which are sold as toys for children. They all go inside each other, but you can also stack them into a tall tower. And of course, in the bath, the babies, small children, can pour water from one to the other. How many of the smaller cup does it take to fill the bigger cup? Think about it, have an answer, maybe later, you know, this is now going up into nursery school. It's still not just play for babies, it's a way of learning. And you don't have to buy something. Caroline has collected together a whole miscellaneous collection of odd containers there. They're all plastic, even that bottle. And there they can play with those in the bath or in a play pool, a paddling pool, or at the beach or wherever. So most of the activity for early years should be free play with water and cups of different sizes, containers of different sizes. And you can enrich their play by asking them to arrange the cups in order of size, from the one that holds the smallest quantity of liquid to the one that holds the most. Now, we're not going to be doing any measuring at the moment. This is just comparing them in order of size and asking how many cups full of the smallest cup fill each of the others. I can experiment with that. It's quite hard to judge just by looking at them. And ask the children to test by pouring from one cup to another. If they've arranged them in order, did they get them in the right order? Of course, with the play cups that you see on the left there, that's very easy and very obvious, but it isn't so obvious with a miscellaneous collection of cups and different shapes and sizes. And as I say, you don't have to spend money on this. You can find, instead of throwing things away, you can collect some. And the children should compare the capacity of cups with their own favorite drinking cup or mug, perhaps.
Okay, so you want to look at this same activity from the lower primary. Then you can start with, before even doing the activity itself, you can ask them to start to arrange in the order. Then instead of using water, you can decide to use maybe sand or rice. And then the learner should work on this activity in pair or small groups with a variety of cups. You can see, just like Tony mentioned in the previous slide, when the cups are the same kind of cups, it is easier for you to be able to arrange them. But if they look different, look at the image in the middle. Are you able to immediately looking at it, whether one container will be bigger than the other? So they can ask them to probably arrange it using basically plastic bottles, so that to prevent accidents in school and all that, and ask them to explore the capacities practically and talk about them. So you can also ask them, now in this case, we are trying to find the capacity full, empty, more than, or less than. So we want to look at, what is the capacity of when it is full, when it is empty. So that is the concept we want to teach the learners. So which one is more than, which one is less than? So ask learners to put the containers in order. Just like I mentioned, before you actually do the activities, before you start testing it, ask them to put it in order. And then when you go about pouring rice or sand inside, and then they pour from one container to another container, then check, were they correct the way they arranged it, the order it has been arranged. So before testing this out and discussing the findings, give learners plenty of time to discuss how the capacities compare and to ask and find answers to their own questions. So that is very important.
And they're learning the vocabulary. And then Caroline.
So on the Aiming High website, which is the resources website for AIMSEC, there are hundreds of resources to help teachers, including inclusion guides that go from early years and from low attainers to high flyers. On those, every teacher resource has one of these diagnostic questions. We encourage you to use these. Now, what you're going to get from this is that every person, you'll be able to actually see just by looking what everybody's thinking. Instead of one person putting their hand up and only getting answers from 2 or 3 people, everybody participates. And you will always be, you'll have A, B, C, or D as the possible answers. So just once they're used to it, you basically get used to putting up 1 finger for A, 2 fingers for B, 3 fingers for C, and 4 fingers for D. And then you can immediately see, and your diagnostic questions will also tell you, when you look at them in the resources, it'll also tell you if they gave answer A, it probably means they're thinking this. If they give answer B, it probably means they're thinking this. So it really helps. There's that resource for you. Please use it on the Aiming High website. So in this particular case, we want you to actually answer it. Go ahead and answer the question. Bottle 3 has, there's 2 words we're looking for, something juice than bottle 1, but something than bottle 2. So there's 2 words. So is it A, is it the 2 words with A, B, C, or D? You can get used to it writing, I think for the text, we may as well just put in A, B, C, or D. If you could answer that, which 2 words match the initial question? And this way you're putting your learner hats on, by the way. This is not your teacher hats, this is your learner hats, having experience and actually using the diagnostic questions. So what questions, I'm going to have a go. Bottle 3 has something than less, okay. Okay, I know, I've got my answer. I'm going to put it in. No, I'm not going to put it in, because what if I've got it right, then it's showing everybody. The idea is everybody shows their answer. You can count 3, 2, 1, go, and everybody shows their fingers at the same time. So, okay, so which is that? A, B, C, or D, Zach?
So we have a comment already. Well, we'd like to get more.
Okay, Talu says A.
Now we have 2 people.
And Zach, you need to say A, B, C, or D.
Well, we've got bottle 3 has less than bottle 1 and more than bottle 2. So A it is.
More. That's A.
Yeah, well, we know you can do that. This is trivial, but the point of putting this on now is that this is a method we use for the teachers to quickly find out whether the children are thinking, whether they're paying attention, and whether they understand what the class is doing. And what we usually do is to do this 1 finger up, 2 fingers, 3 or 4, and then get a learner who's given the first answer 1 finger up to explain why they got it, why they gave that answer, not to tell them whether it's right or wrong, but just thank them for their answer. Then ask if somebody gave the answer with 2 fingers, which was for me, ask them to explain why they gave their answer, and then carry on and ask somebody else who gave answer 3, why did you say answer 3? Don't make any sign that whether it's right or wrong. Having got 4 learners to say why they gave the different answers, or they maybe only give, maybe not of all the answers were given, but however many answers were given, then ask the learners, now you've heard what everybody else said, do you think you were right? Now let's try this again. And that's a way for learners to learn from each other. And of course, by giving an explanation, putting their own ideas into words to actually, straighten out their ideas. So now here, what we call key questions. So one of our strategies, and we encourage you to use it, is to ask questions rather than to tell the learners facts. And so as they're doing this type of activity, you can ask questions. Why do you think that cup's the largest? Let them explain their answers. Or say, well, go into your group, in your groups, talk about why this one is the largest, and then get them to talk about it in groups. Or why is it the smallest? Now there's some open questions like, tell me about your ideas. Why do you think that? Not suggesting that it's wrong, but with an atmosphere in the class that it's good to give explanations, and when you give an explanation, you're helping other people to understand. Why do you think that's the smallest container? How many of cup 3 or cup 8 are there smaller ones will fill cup 1, which seems to be a bigger one? How did you decide on that estimate? Tell me about what you're thinking. So we're not asking you to answer these questions now, but we're just suggesting that they're the sort of questions to ask as the teacher, as the learners do the activity. And if you haven't got enough of the resources to do it, you can ask the same sort of questions as you do a demonstration. How will you test out your ideas? And ask the learners for suggestions, and they can demonstrate what they would do. Why is it important to be able to measure capacity? Now here we come to talking about real life. You know, you buy you buy petrol in liters. You buy anything you buy, you give medicine in small spoonfuls, which are measured in milliliters. So some of these things could be talked about in class. It's not just learning it for the sake of learning it. There's a good reason to be learning it.
Okay, so now we are moving to the primary. And okay, so we want to look at area and volume. So in this case, you have to use square paper and cubes. I want to ask your learners questions. So what sort of question do you want to ask? How many squares? You want to know how many cubes? And then we'll be asking the learner to count the number of unit square. So looking at this diagram, and you ask your learner to count the number of unit square. Okay, and what will the count number of unit cube? So that would be how many square, how many cubes. And I want you to actually write down what is the area of the rectangle. So if you are counting the number of unit square and also the number of unit cube, so what will be the area of the rectangle? What will be the volume? Joshua saying the area of the rectangle is 12 centimeters square.
It's not centimeters, but it's a unit that we're looking at. So we have, as somebody has just said, we've got 12 unit squares, and that's the area. And the important thing here is that we're not doing any calculations, we're just counting. It's easy for you, but we're talking about how you're going to introduce these ideas with very small children by counting.
Okay, so now we've gotten the area. Now, what is the volume?
24 cubic units. It is
24 cubic units. Okay.
And because you've got 2 layers of 12 there. And so you're actually moving from adding 12 plus 12 to multiplication 2 times 12 and connecting addition and multiplication there. This idea between getting used to these words, area and volume, square, unit squares, unit cubes, and all of the language and counting, but not calculating yet. So the area of the rectangle is 12 square units and the volume of the cuboid is 24 cubic units.
Using the pedagogical concept of thumbs up and thumbs down. So again, you can see everyone's answer in the room. You can see what everyone's thinking. Do these models have the same volume, first of all? Yes or no? So your equivalent, if you were working with learners, is they'd be doing a thumbs up or thumbs down. We don't want them to be speaking out because you can't see what they're saying. Whereas you can see a thumbs up or a thumbs down and you know what your learners are thinking. If they've all got it, you can move right along. If they don't, and also you can see if they're looking at each other to see what, if they're not sure and they're looking to get it from somebody else. And always count down 3, 2, 1, go to get everyone to do it at the same time. That's a good way of doing it as well. I'm going to assume that you're going to say yes because they all have 4 cubes. They're all made out of 4 cubes. So I'm going to leave it at, oh, we've got a thumbs up from Mr. Joshua. Good one, Mr. Joshua. Exactly what we want, a thumbs up. And so the next question for those that are, again, you've got the lower attainers, the higher attainers. You can move right on to the next question. Well, perhaps some lower attainers might still be thinking about it. And that is, do they have the same surface area?
You can find the surface area by counting. There's no formula here, but just looking at the shapes and talking about what's at the back and what's at the ends and what's in the top, what's at the bottom, and counting for the surface area, counting the squares. So I think if you count them all, you'll find they've all got 18 square units.
As a surface area, and it's a nice way to introduce the surface area of a 3D shape versus the surface area of a 2D shape. So can you make another model like this with the same volume and a different surface area? So it's a nice challenge. If you can, if you don't have a resource that is made of cubes, this is something you can make. And just, I use dice personally.
And this is something for you to think about. You could put this on the chat because
yes,
this isn't quite so obvious as the last few questions we've been asking.
Well, it's a closed question though. It's yes or no. And
well,
further than yes or no, and actually come up with some suggestions. Go on, Tony.
Well, I want them to see if they can suggest what it would look like. If they made another model like this with the same volume and a different surface area, what would it look like? Still waiting for somebody to answer. Same volume, so it's just going to be made with 4 cubes.
And a different surface area. So you can actually, it is something you can describe with one word. Just, that's a clue. I'm sure you know what it is. But just, I'm going to move on, Tony. Okay, so there you have a cuboid, a 2 by 2 cuboid, 1 by 2 by 2 cuboid, and that has 16 square units of surface area, so it's more efficient. Oh, Zach, counting the surfaces, I'm not sure they have the same surface area. 1, 2, 4, 5, 6, 7. I haven't actually gone through them, but I usually. So we'll check on that, Zach. Thank you.
No, I would really like to know from Zach. Which one do you think isn't 18, Zach? What is the color of the one that you think isn't 18?
Well, Zach says, does the green model have the same surface area as the red model? So I've got on the green model, I see 4 on top, 4 underneath, 4 plus 3 on one end, that's 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. I see 18 on the green and 1, 2, 3 at the bottom. I'm going to count the top ones. 4, 5, 6 up from above, and then along the edges 1, 2, 3, 4, 5, 6, 7, 8, 10, 11, 12, I've lost track.
Well, I think they are all the same, but it's really nice that it's not so obvious, you know. So the red one, there's, if you look straight down on it, there's 3 on the top and 3 on the bottom. If you look, they're actually colored darker red. From the front, you only see 3 that are vertical, and there's 3 vertical at the back. And then if you look at each end, there's 3 and 3 that you can see. So it's the clue here, Zach, and everybody, is that if you've just got contact, you've got 4 cubes, and if you have got contact on 3 faces being glued together, that means that you can do a calculation that way, if you like, because if you've got 4 cubes, there would be 4 times 6 is 24 faces. But if you glue 3 of them together, then that will take off, that will completely get rid of 6 of the edges because they disappear inside. So 24 minus 6 is going to be your 18. And I think if you look at the colored ones there, you'll see that they're attached to each other, or glued together, if you like, on 3 different faces. Whereas the one that is white or not colored, that's glued together on 4 different faces.
And I've also done it using my learner head, my primary learner head, and I've gone round the green and the red. In my imagination, they do have 18 faces, but I had to count the red one 4 times before I was certain, because I kept missing one of the faces. So
and I really like this activity. I really like this activity because, you know, even for us as grown-ups, it's not so obvious. And yet for little children, it's something they can find out by counting. And ideally, we'll hold these shapes and turn them around and look at them from different directions. So let's move on and talk about this puzzle.
The summer cube is absolutely, I'm sure Zach and his team use this. It is so rich in so many ways. It is really worthwhile creating one. Again, I use dice. I have 27 dice that I've stuck together in that pattern. And first of all, what is the same and what is different about the pieces? If you can even get your learners to do the sticking, then they really get a feel for what's the same, how many cubes are there in the different ones, so which pieces have the same volume. You can really get a feel for, okay, if there's more cubes and all the cubes are the same size, all the dimension, edge lengths of, you know, they're all the same size cube, some of them have a different volume to others, and which pieces have the same surface area. So again, you're being super observant and analytical about all these lovely shapes. So before you even attempt to solve a puzzle, you've got a whole lot of vocabulary and concepts. Just the fact that a cube is a cube is a cube, but you add the cubes together, you get different things. You're talking about surface area, volume, and then start solving the puzzle.
And you can, this is a very nice open question, what's the same and what's different? I think that's a really good question to ask in all sorts of circumstances. And here you see some of them are one made of 3 cubes and all the others are made of 4 cubes. You've even got 2 which are mirror images of each other there. And so there's a lot of observations you can make about these shapes.
Which shapes have symmetry, or what kind of symmetry is it, where the lines of symmetry, where is it, what kind, you know, different types of symmetry, is so much there. And this is what you've got to the right is a solution to the Soma cube, which is nice and clear because you've got the different colors. And what you'll find as well, if your learners do this, they actually get super enthusiastic about being able to solve it. So it can be you're overcoming difficulties. I call it perseverance and determination. So you get a lot, they get experience that perseverance and determination, when they succeed, there's such glee. And then they want to do it faster and faster or find different ways. It is such a beautiful activity. And then there are many other types of challenges. This is and on the Aiming High website, on the SomaCube activity, there are, I don't know, dozens, where more than
that.
There are loads and loads and loads of challenges that you can give your learners for all these different shapes. And they can create a shape and give that challenge to their colleagues, their fellow learners. So everyone can create one and then find a partner who can then see if they can create the same one. And there's just so much, so rich. And it's a great way to just wake everybody up at the beginning of maths lesson, or as an after school or lunchtime maths club type activity that just really wakes people up. And there's so many questions that you can ask around it. You can put a challenge. Everybody must make a symmetrical shape. It doesn't have to be a cube. Everyone like make an asymmetrical shape, one that has no symmetry. So many and yeah, I absolutely love this activity.
And of course, if you're lucky enough to have multi-link or centicube, which are plastic cubes which join together, then you can make these Soma pieces from it. My husband made these from a piece of wood. He cut it up, but you have to be quite good at woodwork for that. But it's quite a challenge for older learners if they do woodwork in school. It's a real challenge because you've got to get them accurate. So you've got to get all your saw cuts at exactly the right place and exactly 90 degrees to the edges to make the cubes and so on. So
I use dice, and you also, if you've got a woodworking room in your school, get them to make them. And that's a great activity for them to make, because as Tony's husband Alan explained to me, getting those cubes exactly the right size is no small matter.
Yeah. Again, we're going to ask you a challenging question. So we've just worked out the volume of this one, which is 24 cubic units. So how many other cuboids are there with the same volume? And can you find them? Not just how many are there, but just can you find them? Suggest some cuboids with the same volume. What would the dimensions be? This one is 2 by 3 by 4 and 2 layers of 12, making 24 cubic units, volume of 24. So you want to take 24 little cubes to make it, and 2 by 6 by 2. Well, that would work, wouldn't it? 2 by 6 by 2, another one, 2 by 3 by 4, and we've had 2 by 6 by 2. And there's more. You could have it 1 by 1 by 24. 3 by 4 by 2. Yes, but 3 by 4 by 2 is this one that you see. The top is 3 by 4 and the height is 2. 1 by 2 by
I'm just setting the challenge.
Question mark. 1 by 2 by what?
And the other nice thing with this one is we've got two answers to that. And nice thing with this one as well is you're using the vocabulary, you're using the terminology 1 by 2, even if they're repeating the one that they're actually looking at. You're giving them a way of describing a cuboid or any shape like this, giving them a way of describing it.
2 by 12 by 1. Well, I've got a list here, but I'm not sure I've got everything on it. So there are 24 units, and we're getting more suggestions. I'm waiting for another one. 4 by 3 by 2. 6 by 4 by 1, 24, 6 by 4. So what you actually do, there are 5, I thought there were 5. And there's 5. That's all I could find. And this one that we're looking at, we've seen on a few different slides, is 2 by 3 by 4. But this is all about factorizing the number 24 and splitting it up into 3 factors in different ways. So we're doing some number work in a practical way and linking the number work with the geometry there, with the experience of volume.
Sorry, the other thing there, Tony, is it shows the commutability of them, because you can say it's 12 by 1 by 2 or 12 by 3 by 4 by 2 or 3 by 2 by 4. It's the same shape. But you could also be saying which way up it's standing. So that's, you've got a whole world. The volume's the same, but you've got a whole world of different possibilities of ways of describing it and indicating which way up it is.
And
Yeah,
then
so it seems there's one that we didn't capture, 4 by 3 by 2.
Exactly. Thank you, Tej. It's the 2 by 3 by 4.
2 by 3 by 4 is 4 by 3
No,
by 2.
4 by 3 by 2.
That's okay. So that would be a different way up. So you could actually add that challenge. That depends which way up it is.
But
Yeah.
we're
Include the
just
orientation in the way you describe it, or it's just as long as it's one edge is 2, one edge is 3, and one edge is 4. You've got a whole world within that to
but to be sure that be sure that you've got all the possibilities, and this is cuboids, which Caroline's quite right. I mean, you could change the order of the factors and talk about them being commutative, but if you want to be systematic, you've got 1 by 2, 1 by 3, and 1 by 4. So it wants to be 1 by 2 by 12, 1 by 3 by 4, 1 by 3 by 8, and 1 by 4 by 6, and those are all give you 24. But then if you go, you can't use 5, and if you go 1 by 6, then you're back on the one that you've given there, 1 by 4 by 6. So that's all of the possibilities with a 1 in them.
Actually, I agree with you, Tony, that 2 by 3 by 4 is the same as 4 by 3 by 2. Yeah.
Yes, exactly. And so then, having started with the 1 and seen that there's only 3 possibilities, not just that I couldn't find any more, logically I knew there couldn't be any more, because we tried them in a systematic order. Then we go we've had 2 by 1, so we won't repeat that. But now we go 2 by 2, and that must be 2 by 2 by 6. And then we go 2 by 3, and that's 2 by 3 by 4. And then there are no more possibilities, because if you go on to 2 by 4, you've already seen that, and so on. So
you're leaping to that, Tony, but a young learner or even an older learner who's a low attainer will actually write out all the 1 by 6, 1 by 8, and 1 by 12 and take it round that way. And they'll move on, and they'll have the third column with 3 bys, so that they like the idea of being systematic. And then they'll have 4 bys, and then they'll work out they can't do 5s. Then they'll have 6 bys, they'll have an 8 by, and they'll have a 12 by column. What you've then got is a beautiful framework to help them recognize that they've already got 12 by 1 by 2 or 12 by 2 by 1. They've already got it, and it's actually a way that they go to the effort of writing it all out. You can then help guide them, or they can work with a fellow learner to see that they've actually already got that. They can narrow it down to just those 5 possibilities.
Well, Caroline's absolutely right there. And this is a lovely way to introduce the idea of commutativity. You've got these different descriptions, 4 by 3 by 2, as Tejabade says, which seems like a different description to 2 by 3 by 4. And as Caroline says, if you turn it round and you put the not in the order of increasing numbers, but factors that increase, but by the height. This is the height by the width by the length, 2 by 3 by 4. But you can ask the learners, well, are any of the ones you found actually the same cuboid? And then they can sort them out and find eventually that there really are 5, and that to be sure there are 5, you have to be systematic. So I think this is a very simple activity, but it's actually got quite a lot of potential as something that to explore and talk about. And now then we're leading on to the surface area of this. What is its surface area? So now we've got to look like we did with the where we had shapes models with 4 cubes. We've got a lot more cubes now, but it's a much simpler shape. How would we find the surface area? Well, we need the top and the bottom, each 12, the front and the back, each 6, and the red side and the other one opposite it, which are 8. So there we have. The top is 12 square units. What we see as the front is 6 square units, and the side is 8 square units. And so it's 2 times 26, which is 52 square units.
Yeah, so now we are looking at the same volume, different surface areas, and you can look at this from the upper primary. So we want you to look at these 2 images, just look at them. Now, if you have 2 shapes with the same volume, do they have the same surface area? Thumbs up, thumbs down, and you can use the charts. They have the same volume. Do they have the same surface area? 6 by 2 by 4 and 3 by 2 by 8.
At the last slide, we looked at the same surface area and different volumes. Now we're going to look at the same volume and different surface areas. You could just guess whether it's yes or no, or you could do some, maybe you'd be quickly calculating that those 2 cuboids have got the same volume. Do
Okay,
you
I
think
can see Caroline said she's not in agreement with this. Yes, it's a no as far as she's concerned. Does anybody have a different opinion about that? Do you think they have the same surface area? Okay, Joshua also says no. All right, Talu also says no. All right, so now we're going to be going forward. All right, so for the volume, so let's look at this. We have 8 plus, just like we counted now, that is 8 plus 12 plus 24 times 2. So let's look at it. And
that's
then that
the surface area?
The surface area, yeah. So the surface area gives 88 square units, while the volume is 48 cubic units. 48 cubic unit. Okay, so let's see the second one, the second image. So that would be 6 plus 16, which is the surface area will be 6 plus 16 plus 24 times 2. That gives 92. And look at the volume. When you look at the volume of both, they are the same. However, the surface area totally different. So they are not the same. So it means when they have the same volume, it is not automatic that they will have the same surface area.
Now, let's look at the same question the other way round. Okay.
So we've got on the left, you've got your guide for what we've just done. So you've got that as a visual reference. Again, put your learner head on here. So you've got that as a visual reference. And now we have another question. Tony, how many cuboids have the same surface area, the same 52 square unit surface area? How many, can we have the dimensions? Oh, we've got, Tony's given us some dimensions here. So that one, we hope has 52 square units. Are there any others? The question is how many cuboids? So we've got an open question. It isn't, well, I suppose it's an open question. We don't know how many. So we want the learners to actually go through the process and see how many they can work out. We've worked out that there are 5 possibilities. So of those, we can work with the 5 that we've got, because we now know there are 5 possibilities. So work out now we worked it out, that is the 1 by 2 by 8. What is the volume and surface area? So again, put your learner head on here.
Did you work out that the volume of this cuboid here is 1 by 2 by 8, which is a volume of 16 cubic units, and the faces are 2 square units, 8 square units, and 16 square units. So that adds up to 26, and then the 2 faces of the same area, and so the total area is again 52. So there's one example, and that's the only one I could find, but maybe somebody else will find another one that's actually the same the same surface area and a different volume. Now here, these are some little shapes that you can make with cubes, and this is an important idea, that if you double the edge lengths, what happens to the volume? Now, I think you all know and you can see, but it's so nice. It seems so, just doubling the edge length, what's going to happen to the volume? Well, you get 8 times the volume, and the picture there shows you, but it was even better if you can make the 2 little models and compare them. And so what you have got here is the 3D object is of twice the height, is 8 times the volume. And now we're in secondary school. The first hour was mostly primary, and now we're in secondary school, and we're talking about scale factors for enlargements. And the linear scale factor, because we're doubling the lengths, is 2, and the area scale factor is 4. And if you look at the front of those L shapes, you see there's only 1 square on the one on the left, whereas there are 4 on the one on the right. All the areas are multiplied by 4, and the volume is multiplied by 8. So those are the scale factors. So that's a little bit more work with cubes that you can do. And you can talk about the word capacity and link the words capacity and volume, that the capacity refers to the volume of liquid that will fill a container.
Jumade?
Okay. Yeah, thank you. So now, just like the what Tony just mentioned now about capacity, then so that linking it with volume. So mere looking at these images that we have, you can use measuring jug, okay, to show the learners how to find capacity of cups in milliliters. So on the cup that we have on the left side of the page, so you can see it's calibrated, it has the measurements written there. Now, so now you want to introduce the idea of a liter and the meaning of the word milli, which means 1,000. I want to discuss it with our learner. So when you see 1 cubic centimeter is 1 milliliter, and also 1,000 milliliter is 1 liter. So if you look at it, how it is calibrated, you can easily see that 1 liter corresponds to 1,000 milliliter on that cup. Now, so ask learners what is measured in liters and what is measured in milliliter in everyday life. So we can actually look at it. What is it like? You go to a gas station. Now, what are you going to ask for? Are you going to be asking for milliliter? I want 20 milliliter gas. Or, okay, you want to give your child medication. Are you going to be giving your child in liter? So now, so you can ask them on everyday life, what is measured in liter, what is measured in milliliter.
And Teshumada, in the kitchen, when we're doing cooking, we tend to use both, don't we? Because we have liters of milk, But when we are measuring ingredients, like, you know, if you're going to put some flavoring in a mixture, you're likely to put it in by a teaspoonful at a time rather than a larger amount. So in cooking, you sometimes use milliliters and sometimes you use liters.
Yeah.
But because it's 1,000, we're talking about thousands, it's a little bit maybe difficult to get your head around. And Caroline's got a nice demonstration to show us the idea of a 1 milliliter and 1 liter, which is 1,000 cubic centimeters.
Going to show you first, because we did the 5 milliliters at first, which is a teaspoon. This one is 1.25 milliliters, which is just a little bit bigger, well, 1.25 of the cubic centimeter. So that's just to follow up on what Sejamada said. Now, we've got 1 cubic centimeter. I have prepared earlier a box that I'm not going to tell you yet what the dimensions are, but hopefully you can work it out. Here's the box. You can just tell us what you think the dimensions are of this box if you're in the chat, if you've got a moment. And that's a lid. That's my lid, so that you can actually see. I'll give you, this is one of my favorite things. You put this little guy in here and actually see the size of the cubic centimeter compared with the whole box. Okay, so it's a 10 by 10 on every face, which means that it's a 10 by 10 by 10, which makes it, I know it takes time for the information on the chat to come through, so I'm just going to say it's 1,000 milliliters. Now, 1,000 milliliters just happens to be that lovely quantity. I'm in the United States, so they don't have liters here, but they did find the Pellegrino from Europe. Each one of these is 500 milliliters. So these 2 bottles, when full up to about there, have the same capacity, or the capacity as the volume of this shape. So this is actually 1,000 milliliters, and these 2 bottles together hold 1,000 milliliters. Just
so that's, Caroline, it's 1,000, yes, you're right, but it's 1,000 cubic centimeters.
This is 1,000 cubic centimeters, but if I were to fill this with water, thank you, if I were to fill this with water, it would hold 1,000 milliliters. And that is by definition, that is not a coincidence.
But Caroline, when I see that demonstration, yes, I'm thinking, really, when I fill up my petrol and I'm paying a lot of money for a litre, and a litre isn't very much, really.
That's it. Look, I can hold it in the palm of my hand, a litre. I don't think I want to hold a litre of petrol in my hands. I think it would all run through my fingers, but yes, that's not a whole lot. And that's, yeah, it's just 2 of those. That's it. What you're paying for a litre of petrol. So now this again, put your learner hats on, and we'd like the answers to these questions. So under each cylinder, on the top line, please write the number of milliliters in the cylinder above it, and on the second line, write the number of liters in the cylinder above it. And so this is the first one. You're given the first one. It's 500 milliliters, which is 0.5 of a liter.
So this is part of a worksheet that's on Aiming High, and we're going to give you some links. So it is something that you could show the pictures to the learners and get them to have practice in reading scales, because it is an important skill. And as I said earlier, you know, I'm not sure whether we're doing maths or science. There really isn't any difference between them. They're one and the same, aren't they, really, at this level? So you've got 8 answers to give there. You might like to give them 4 and 4. what you'd put on the top line, and then what would you put on the second line?
I'm going to cheat. I'm going to just put what you've already said. So I'm just going to get the ball rolling by doing that.
You've done 500 and 0.5 for the first one. So that's the first box rather than the top line. So what would the second box be then, if you want to do it that way, Caroline? That's
All right, this is
100
Joshua.
and 0.1. Good, Joshua, well done. And what's the third box? This one's an easy one, really. 2,000 and how many liters?
2 liters.
Yeah,
2
thank
liters.
you.
Alu.
And the last one is there on the screen now. Okay, so that gives your learners, that worksheet gives your learners an opportunity to practice reading a scale. And actually on the worksheet on the Aiming High website, there are 8 examples. There's only 4 here.
I would like to point something out here that I broke my own rule here, because I don't ever allow my learners to just write a number. Now on the sheet there, it does specify within the text that it's milliliters on the first one and liters on the second one. But when we were writing the answers just separately on the chat, I, following my own rules, I should have written ml and L after those numbers, just because
It's a good habit to get into.
It's good practice.
Yeah, that's right.
And the thing is, the learners, unless they get into the habit at the beginning, never get into the habit.
So here, I just wanted to bring this to your attention. I actually got it from the American Academy of Pediatrics, the website, which was for healthy children. Okay, so advice to families, advice about medicines and how to administer them. And why is it important when you can ask your learners to be able to read scales? Well, of course, in every household, people need to be able to give medicines when necessary and give the right doses, and mix up if it's for babies, mix up the baby food in the right proportions, whatever. So the best practice is to measure in milliliters as read on the dosing device. And you see the little pictures there. 1 tablespoon is 15 milliliters. Well, in America, they used to measure everything in teaspoons and tablespoons, and that's the relationship between them. And most households have a medicine spoon, which is usually 5 milliliters. But there's a syringe there, which is also a way, or a dropper or a syringe, where you drop the medicine down the back of somebody's throat carefully, the right place so they don't choke. But you can see there the marker for 5 milliliters on the picture. And this, some of your learners may well go into nursing, and all at some time or other in their lives going to be caring for sick people. So it is important to be able to read scales and get the dosage right.
All right, so looking at this, so I just wanted to imagine a large cube, which is 3 by 3 by 3. So it's made from 27 small red cubes, each measuring 1 centimeter by 1 centimeter by 1 centimeter. So we have 27 small red, and each of them is 1 centimeter by 1 centimeter by 1 centimeter. What is its volume? What do you think the volume will be? What will be the volume? We've been doing a lot of counting, asking you to count the small cubes. Now, imagine dipping the large cube inside a pot of yellow paint. Just look at this image, look at this. So the first one we have there is red cubes, and there are 27 of them. Now you now dip it inside the yellow paint. So the whole outside surface is covered. Now the surface is covered. What is the surface area? Now I want to imagine breaking the cube up into 7 small cubes. Now they are broken down. If you look at the other image that has one part removed already, so we can see red inside and then yellow outside of it. How many of the small cubes we have yellow paint on their faces? How many of them? How many we have? They all look the same. So let's just imagine those ones that have they have the red paints in with them or the yellow paints on the surface. Will they look the same? And I want us to use the chart. Are they going to be the same? How many yellow faces do the corner cubes have? So you can start thinking about it. How many yellow faces? So when you look at the ones at the corner, the cubes at the corner, so how many yellow faces do they have? How many faces on the other cubes are yellow? So from this small exercise, you can see we have a lot of activities or a lot of questions we can derive from it. So I want to now imagine doing the same with other big cubes made up from small red cubes. Do all the same cubes have yellow paint on them? Do they all have yellow paint on them?
So it's a very nice problem, and it's one which you can generalize to 4 by 4 by 4 and 5 by 5 by 5. So Tejamad has asked you some questions, and maybe you'd like to put the answers. What is the surface area was the first question of the outer of the red 3 by 3 by 3 cube.
And probably you also discover some interesting stuff. What have you discovered?
I think you can, as experienced teachers, you can probably imagine that there's quite a lot of questions to ask. We've asked some of them here, quite a lot of questions to investigate, think about and talk about. So do you remember early on we talked about doing something, talking about it and recording your results? And on the next slide, we're going to show you some of the answers. But see the next slide for the general answers. But here are some of the answers. I'm sure you could get these right yourselves. The surface area, 54 square centimeters. Where does this mysterious answer of 26 come from? Because there are 27 cubes altogether. Can anybody explain why there's only yellow paint on 26 of the faces?
Put your learner heads on. It may be obvious to you, but think about the huge realization it is to some learners to figure out where that missing cube is.
Okay, and what result do you get for 4 by 4 by 4 and 5 by 5 by 5? So we are going to look at that on the next slide. But you can also go to our MEI website for their links. When you are talking about this painted cube, is actually picked from MEI website, so you can get more detail from there as well.
And the links will be provided at the end of the session. So this one is very much a low entry, high ceiling activity. The low attainers can work on maybe just the 3 by 3 by 3 cube. You could even bring it back and make it a 2 by 2 by 2 cube. And it's yet still allowing the high flyers to go all the way to the generalization. Now, some of the things that we're looking for here, there's so many possibilities here. We really want everyone to come up with something or more than one thing. We're looking for the number patterns. We're looking for number patterns. We're looking for the formulas. You don't have to go to the formula. Is there any particular column that has something interesting happening? For I find column number 5 quite intriguing. As a putting on my learner head, why is number 5 all the same and all the others are different? And you've got numbers that you're familiar with. We're looking for square numbers, we're looking for cube numbers. And why are those square numbers and cube numbers there? So what can we see? There are so many, there is no such thing as a wrong answer here. Well, there's no such thing as a wrong answer anyway, because every time you answer a question, you learn something. So what patterns can you see? What patterns do you think, again, put your learner heads on, what patterns would help your learners?
So in the top line, you've got the fact that right inside the 3x3 cube, there's just one little cube which doesn't have a yellow paint on it because it's right in the middle. But when you have a 4x4x4 cube, there will be a 2x2x2 cube in the middle that doesn't have yellow paint on it. So there will be 8 small cubes which end up with all faces red and nothing yellow inside a 4x4x4. And that's why you've got cube numbers in column 2. But there's a lot of exploration here in these sequences, and finding a pattern in the sequences that corresponds to a pattern in the geometry, and leading on to the algebra that finally you have the general answer in a formula. So as Caroline says, I mean, Caroline was talking about this as a low entry, high ceiling activity. Does allow every learner to be doing the same thing and working on the same problem, but some of them taking it further along the road than others. Now, compared with this activity, the next one is rather a simple activity, really. Not a practical activity about packing. So there's a company that makes tops. There's a little picture of the top. And you have to design these spinning tops made from 2 pieces glued together, which are a hemisphere and a cone. And then you put them in little boxes. And you have to plan how they'll be manufactured, packaged and sold. So you've got the radius R and of the circular surface there, where the pieces are glued together, and that's 3 centimeters. And the slant height S of the cone is 5 centimeters, and you got to work out the total height. Now, maybe your first thought, maybe your students' first thought will be Pythagoras' theorem for that little triangle, but they should spot that that's a 3, 4, 5 triangle and immediately say, oh, well, the height of that cone on the top is 5 and the radius of the hemisphere, the half a sphere, is 3, so the height is 7 centimeters. So these tops are 6 centimeters across and 7 centimeters high. And so you're designing these and you pack them in a box, and the box measures 6.5 by 6.5 by 7.5 centimeters. So the little top fits easily into the box. And so those are the very small boxes. And now they're going to be put into packing cases, and the packing cases are 55 centimeters by 55 centimeters by 55 centimeters. So here's a problem for you. How many of the small boxes will you fit into the big box? Now this is only packing cuboid shapes in a big packing case, which happens to be a cube. How many? Would you like to have a go at working that out? It's a practical problem. How many of the little boxes could you put on the bottom of the packing case? They measure 6.5 by 6.5. How did we come up with 64 boxes in each layer? Why? So twice times 6.5 is 13. And if you've got 8 times 6.5, that's going to be 4 times 13, which is 52. So if your case measures 55 by 55, you can pack in your bottom layer, you can do 8 by 8, which is 64 boxes in each layer. And then will you be able to put 8 layers in? Work that one out. You'll find that because you've got 7.5 there, it's how many 7.5 so you're going to be able to put in to how many layers. And 7 times 7.5, 49, and 3.5 is 52.5. So you've got a little bit of space there. You can't squeeze, it wouldn't be a good idea to squeeze them in with no space. It's just a few millimeters between. So there's we've gone through that fairly quickly, but there's one that you could your learners to explore in working groups and work out what the answers would be there. 7 layers with 64 in each layer. Now there's more to this problem. This problem, going back to this shape, this spinning top, which is a cone and a hemisphere.
Now, so looking at this, we want to investigate the volume of cone. And then now this activity will prefer that you cut out this your own cone, just make a cone. And how do you do that? Now from the circle, so you cut out, you can see the image that is there, and we have 216 degrees for that angle that is there. Now, so what you just need to make sure is that the paper you are using has the same, the length, the height is the same as the cylinder that you are going to use. So make your own cone and cylinder the same height from paper. You can make it from plastic. You can use scrap card and using the templates. Now, fill the cone with lentils. You can fill it with rice. You can fill it with anything that you know that it will be easy for you to pour. Now, something similar, or investigating the relationship between volume of the cone and the volume of the cylinder. So basically, you want to investigate, you want to see.
Caroline's going to demonstrate it.
Okay, so we have a cylinder and a cone. Now, the critical thing is that they're the same height. So I've made mine with cardboard, so they're not perfect circles or anything, but they are made with the template that you'll be available to you at the end of this. So they are the same height. And what I'm going to do is I'm going to do exactly what Tej just said. I'm going to fill my cone. Whoops, let me get my tray. Contain the mess. Fill my cone with rice. They're the same height, and they have the same diameter. Pour that into the cylinder. Whoops. There's 2, that's 1 and 2, and 3. Now I've got some spillage. There's some captured in the tray. You can transfer it back in again. Basically, that demonstrates, without having to actually do the maths required, that for the same height, the volume of a cylinder, the volume of the cylinder is 3 times the volume of a cone with the same diameter.
Okay, so we can see the volume of a cone is 1/3 of the volume of the cylinder. Now, most of the time, yes, the learners just memorize, but if you are able to show them these experiments or do this experiment with them, then it becomes very easy for them to know what you are talking about. So look at it, it's very easy and straightforward, but you just need to make sure that it is the same height. And we saw how Caroline was adding them, putting it together, and we could see that 3 going inside the cylinder, 3 cone will fill in the cylinder. So the volume of a cone is 1/3 of the volume of the cylinder. So volume of a cylinder is pi r square times height, pi r square height. And the volume of a sphere. Now, Tony, where are you? Are you close by?
Yeah.
Oh, okay, good. I just wanted to add you because I know you have something to add to that.
Okay, well, all I was going to say, this isn't a proof of the formula, although it's convincing, it's good evidence of the formula, okay? And actually, you'd need to learn integral calculus to prove the formula, but it's a formula that children learn in school and they have to use it. And it goes against the grain with me a bit because I really rather like to only introduce formulae when we can actually prove them. At least this one you can demonstrate. So I like this demonstration. And the volume of a sphere is 4/3 of pi r cubed. Again, that's one that learners meet in school and use in school, and it's not until they do integral calculus, which of course they do in some schools, that they work out these volumes, and certainly something that is taught for age 17, 18-year-olds, but in many schools it's not.
Tony, can you leave the slide on just for a moment? I'd like to add as well that this is a perfect activity for do, talk, record. Get the learners to make them, the templates is supplied to you, make them, do the measuring, and then talk about just give them the formulas, because that's all you can do it for this one. Is you can't, it's advanced. It's not meant for secondary level learners. It could, yeah. So do the activity, have them do it. Don't do it for them, if possible. Have them do it. They talk about it, they learn from it, they record it, and then you give them the formula. That's my thoughts on the matter. And before we move on to the next slide, I'd like you to notice the shapes that Tony has made above. She's made with clear plastic. Tony's used the template. Well, this is slightly different. Those are different dimensions, but it's the same shapes. And what she's done, she's used scrap clear plastic. She's found a container or a box, something that was that clear plastic, and she's wrapped tape around it so that you can actually see inside, and it's also nice and round, and like the one I made. And the cylinder again is nice and round and clear. You can see everything inside, no mysteries.
So actually it was the same size, Caroline, but it's only obviously it's a picture shows it a lot smaller.
Yeah, I couldn't see the dimensions. I thought the dimensions were different. So what I've got here is simply, if we could just spotlight my visualize just for a moment. We've got I've literally just cut these out of the resource that's supplied to you, and it's a worksheet on the Aiming High website. We keep mentioning the Aiming High, please use it. So the cylinder you just make by cutting out the circle and the rectangle. A beautiful demonstration. Again, do talk, record. to show learners how the formula for the cylinder works. It's simply a rectangle plus two circles. And for this activity, it doesn't have a top because we're pouring in the rice or whatever you're pouring in. But you could make cylinders. Your learners could all make their own cylinders as a do, talk, record activity with the top and the bottom circle. And then they have solid cylinders using this same resource. And it's the other thing I liked about this. You've got the dimensions that Tony's used, got 3 centimeters radius, and here the circumference of the circle is 6 pi. So 2 pi r, 2 times the radius times pi is the circumference of this circle. So I think that's a very nice, simple way of experiencing the circumference of the circle to add into this whole activity. And the cone is quite simply, it's the same height. So you've got 6 pi centimeters because you're making it into a cone. So this arc is still 6 pi because it has to be, so that the base of the cone is the same as the base of the cylinder. So you can do the one-to-one comparison of the volume. And again, 3 times the volume of the cone is the volume of the cylinder, which I demonstrated earlier. There you go. There's our cylinder full of 3 times the contents of 1 cone.
Yeah, we kept mentioning the EMEA website. So on the EMEA website, you have free content that you can freely download, workbooks, worksheets that you can download. So it has teachers' content that with solution for your learners. So you have questions, diagnostic quizzes that you can use, formative assessments. And we also include inclusion and home learning guides and the activity. So they are rich content, they are rich materials that they are freely available. So you can download, you can make copies for your learners, make use of them. And you can also get ideas, even when you are preparing your lesson plan, then ideas of things to do, activities, so that your class will no longer be boring. So they are available. And these are the links to the cups and capacity that we've talked about, bottles and capacities, painted cube tops, some cubes, and much more. A lot of information are available there. So we want you to go and make use of them. Yeah, please visit EMEA website. Yeah.
So
bye.
Try and help your learners to have the yes I can attitude to maths. Okay,
We can make that our
everybody.
slogan every time. Thank you. Goodbye.
Bye.
This is a Global Teacher Empowerment Network video collaborating with AIMSEC and the Aiming High website. Our mission is to benefit children in disadvantaged communities all over the world by empowering the teachers who teach them mathematics.